Hello everyone, welcome. This is the first event of the new year, I guess of the second half of Encode University Hackathon. We are joined today by Dan, who's a senior software developer at Avalanche. We've already had one presentation by Gabrielle in I think that was in November, and we were treated to the delight of having Emin Gunsira, Professor Emin Gunsira, give an AMA. In I think towards the end of November or early December, which was truly fascinating. This should be a chance to get another deep dive into Avalanche as we reach the kind of next few weeks and the submission time for the hackathon. So please do listen intently. Please do ask any questions you have, principally on chat. I think that usually works most efficiently. And yeah, hopefully we'll have a very nice event here, guys. We'll run, I guess, about an hour, probably. Split between the presentation and some questions as well. Well, Dan, look, great to have you. Thank you for your time, and handing over to you, sir, to tell us more.
Sure. So first, thanks for having me. As Anthony said, my name is Dan Laine. I'm a senior software engineer at Avalabs, the company that is developing the Avalanche network. So this presentation is going to be a deep dive into the Avalanche consensus protocol. I'm going to stick pretty closely to just stuff about the consensus protocol itself and not the other facets of the Avalanche network. I'm, as noted, not a very proficient Zoomer, so my apologies for any technical issues that arrive. And I will also note that I am not one of the team's consensus experts per se, so my apologies for any mistakes or omissions during the presentation. So with that, let's get into things. So first, let's try to just get some intuition about the way that the protocol works. So suppose that you're in a room of people, I know a kind of unthinkable thing at this time, and everyone's trying to decide what to get for lunch. And it's a binary decision that you and the group are making, and you're trying to decide between pizza and barbecue. And everyone's goal is just to get everyone into agreement on what to pick. Everyone might have some initial preference. Maybe they want pizza, maybe they want barbecue. But at the end of the day, really what they want is to just get everybody on the same page. And let's suppose that there's no leader that can kind of move things along. It's kind of a democratic process, and everyone's trying to just get the whole crowd to agree without doing like a shouting to everyone and everyone shouts back sort of deal. So let's say that you walk up to a few people at random in the room and you ask them what they prefer. And of the few people that you ask, they all say the same thing. They all say pizza. So you do this again. And again, everybody says they think that the outcome is going to be pizza. So you do this a few more times, and again, almost everyone says pizza. So at this point, you're feeling pretty sure that the feeling of the room is that the outcome is going to be pizza. So you do this again and again and again, and eventually you're going to be pretty confident that pizza is the outcome that's been decided. So that's the intuition for Avalanche. So let's get into a little bit more specifics here. So I'm going to walk through this algorithm, which is called Snowball, step by step here. So don't be daunted by the wall of text. So at the start, you have some preference, and maybe it's pizza, maybe it's barbecue, whatever. It doesn't really matter that much. So until you've decided on what the outcome is, and you arrive at your decision in a sense, independently of everyone else. Everyone else is following the same algorithm, but they might decide slightly before or after you. So until you've decided, you go up to a few people, just a handful, which is a number that we call K. Maybe it's, I don't know, 10 or something. And you ask them what they prefer. If a sufficient portion of them give the same response, you adopt the preference that got the majority response. And we have this other parameter called alpha, which is the quorum size, we say. So if greater than or equal to alpha of the people that you ask give the same response, you're going to adopt their preference. So if you already preferred that option, you're going to increment what we call a consecutive success counter, right? So that's consecutive successes plus plus. If the alpha majority response you got was different than the one that you had before, right? You preferred barbecue, and then you asked a bunch of people and they all said pizza, then you're going to adopt pizza as your preference and set the consecutive successes counter to 1. If you're not able to get a quorum, an alpha majority of the same response, then you set the consecutive successes counter to 0. So you do this over and over and over again, and everybody else is also following this algorithm at the same time. And if you keep getting the same alpha majority response when you subsample the group, then after a certain point, you can be confident that everybody else prefers the same thing. And that if you decide pizza, for example, everybody else will eventually decide pizza, and no correct person will decide barbecue. Okay, so I hope that was pretty clear. So this is the Snowball algorithm, and this is the building block of the Avalanche network. And here's a video that for some reason doesn't want to play to me, so I'm going to go into the next tab. So what this is a visualization of the Snowball algorithm in effect. So the network is going to start in a bivalent state, which means basically it's undecided between the two options, which in this visualization are orange or blue. And each one of these squares represents a node in the network, right? Someone trying to reach consensus. So I'm gonna reset it here and hit run. And at the start, we can see that some of the nodes are orange and some of them are blue, and they're querying each other just according to that algorithm that I showed a second ago, and updating their preference accordingly, right? So you could see that at the start, even though some were orange and some were blue, just random perturbations in the network, because you're sampling from the validator set randomly, you just get a preference on the network a little bit for blue in this case, and then that reinforces itself, right? Because if you've adopted blue as your preference, and someone asks you your preference, you say blue, and then they're more likely to adopt blue, and so on, and it kind of snowballs, if you will, into this state where the decision has kind of become irreversible, and you're just on like a path to blue, and nothing can stop the network from going to orange after a certain point. And then once the nodes are sufficiently confident, they've done enough consecutive successful queries, then they reach a decision. So a cool thing about this simulation is that you can actually click to try to change the color of the node. So I'm going to try to make the decision orange, right? So now orange has taken hold, and now even though I'm clicking to make these nodes blue, it's not enough to overcome kind of this avalanche effect or snowball effect, if you will, to get the network to go to blue. So even if there's people that are behaving maliciously, it's not enough after a certain point to get the network to adopt what they want. Okay, so random noise in the network because of the random sampling yields some increased network preference for one choice, which begets more increased network preference for that choice until it becomes irreversible, and then the nodes can decide. Okay, so Snowball generalizes to multi-value decisions, not just binary ones, right? Like we had pizza or barbecue, that was a binary choice, or blue or orange. But it turns out that actually this generalizes to multi-value decisions where you can be deciding from not just two things, but many things. So one thing to note is that the liveness and safety thresholds of this algorithm are actually parameterizable based on the parameters that you give it. So as you increase the quorum size, this parameter alpha, the safety threshold increases and the liveness threshold decreases. So what that means is the network can tolerate more Byzantine nodes and remain safe, safe being all eventually agree on whether something is accepted or not. And as you increase beta, the number of consecutive successes that you need before accepting something, as that increases, the safety threshold increases and the liveness threshold decreases. The liveness threshold is the amount of malicious participants that can be tolerated and still make progress towards making a decision. So these numbers are constants, and they're actually pretty small. So on the Avalanche network right now, the value for K, the sample size, so when you ask a group of nodes what their opinion is, you only sample 20 of them. The quorum size is 14. So if 14 or more give you the same response, then you adopt that as your preference. And the decision threshold is 20. So you need 20 consecutive responses the same way in order to decide on something. So something that's really cool and that I'll come back to is that this is super scalable as the number of nodes in the network increases, that's actually pretty cool, because regardless of the number of participants in the network, the number of consensus messages that you need to send stays the same, right? Because you're only going to query at a time 20 nodes. So it doesn't matter if there's 20 nodes in the network or 2,000 nodes in the network, you're going to send the same number of messages. So I'm going to introduce a data structure called a DAG, or a directed acyclic graph. And you all might be familiar with these, but I'm going to go through a little bit of stuff about them just for completeness. So a DAG gives a partial ordering of things, right? So in this example, A is before B because there's a line from A to B. B is before D because there's a line from B to D. And similarly, D is before E. So transitively, we can say that A comes before E, but this is a partial ordering. And what that means is that for some things, the ordering is not defined, right? Like B is after A and C is after A, but there's no notion of whether B is before or after C. Okay, and two other pieces of terminology that I want to introduce are ancestors and descendants. So ancestors is basically everybody that you can draw a line up to in the graph. So the ancestors of D, for example, are A, B, and C. And the ancestors of E are, you guessed it, A, B, C, and D, because you can draw a line backwards to any of those. And the descendants are the opposite of your ancestors. So the descendants of A are B, C, D, E, and we're going to see why that's important in a minute. So Avalanche uses a DAG to store things as opposed to a linear chain, right? Like Bitcoin or Ethereum, there is a chain where everything has one parent and one descendant, and Avalanche has a DAG, which means that something in the DAG can have multiple parents. So a common source of confusion is the parent-child relationship in the DAG does not necessarily imply an application level dependency. This is just something that we kind of use to move things along in consensus. So for example, just because B is the child of A does not mean that B's linked to A in the application. Like for example, if this is a peer-to-peer payment system, B doesn't necessarily spend a UTXO created in A or anything of that sort. Okay, so with consensus protocols, the name of the game is to prevent bad things from happening and to make progress when bad things aren't happening, or to just make progress, period, I guess. So we want to prevent the inclusion of conflicting transactions in the DAG, and conflicts are application defined, right? So like different applications will have a different notion of what it means for two transactions to conflict. In a peer-to-peer payment system, for example, which is obviously very big in the crypto world, for example, two transactions that try to consume the same UTXO are defined as conflicting. So in Avalanche, we have this notion of a conflict set, and transactions conflict set is, as you might guess, the transactions that conflict with it, right? only one transaction in a conflict set can be accepted, or else your protocol is broken. Okay, so let's see how Avalanche works. So suppose that we've got this Avalanche network running, and the sample size is 4. The quorum size is 3, right? This is the alpha majority response that we need. And beta, the number of consecutive successes that we need, is 4. So here's some happy node here. And he finds out about a new transaction called Y, and it queries the network, right? It picks K validators, and it says, do you prefer this transaction? And we'll get to that in a second, what preferences. And it gets its responses, and 3 of them say, yes, I prefer this transaction, and 1 of them says, no, I don't prefer that transaction, right? So alpha is 3. So we have an alpha majority because we have greater than or equal to 3 yes responses. So now we're going to update the DAG, which is this data structure that we have locally. And I know there's a lot here, but I'll break it down. So if you get an alpha majority yes response for a transaction, you give that transaction what we call a chit. A chit is just a Boolean or a 1 or a 0, if you want to think of it that way, that says, when I queried the network about this transaction, an alpha majority said that they preferred it. So transaction Y here, we give it a chit. And there's also this notion of confidence. And confidence is the sum of your chit, 1 if you got a chit or 0 if you didn't, plus the sum of all your descendants' chits. So let's look at this graph. So transaction V got a chit, and it has 3 children, or 3 descendants, I should say, that got chits. So its confidence is increased from 3 to 4. Similarly for transactions W and X, they both have a chit, and they both have a descendant with a chit, so each of them have confidence 2. And transaction Y has confidence 1. And we also have this consecutive successes counter, which is, well, I suppose we'll see that in a second. But it's the same notion as in Snowball. The number of times that this transaction or a descendant of this transaction received a successful alpha majority query, right? So before, transaction V had 3 consecutive successes, right? Itself and its 2 children. And now it has 4 consecutive successes with transaction Y, and similar for W and X. So the algorithm this node follows is it got an alpha majority response of yes votes. So it gave transaction Y a chit. It incremented the confidences of its ancestors, and it incremented the consecutive successes counter of its ancestors. Cool. So now, remember that we had beta, the number of consecutive successes required for a decision. We had that set to 4. And now transaction V has 4 consecutive successes, so it's accepted. Okay, so now let's say our node learns about some transaction Y prime, which conflicts with transaction Y. And we do the same thing as before. We randomly subsample 4 validators on the network, and we ask them if they prefer transaction Y prime. And in this case, 2 of them say, yes, I prefer Y prime, and 2 of them say, no, I don't prefer Y prime, right? So this time we didn't get the alpha majority response. So what do? We update our DAG accordingly. So transaction Y and Y prime are in a conflict set, right? We said that they conflict with each other. Only one of them can be accepted. So we're going to say transaction Y does not get a chit because it didn't get an alpha majority response. It has confidence 0 because it doesn't have a chit and it has no descendants with chits. It has 0 consecutive successes because that query that we just did for it didn't yield an alpha majority response. And then we update all of our processing ancestors, which in this case is just transaction W. So its consecutive successes goes from 2 to 0. The confidence is still 2. This is an error. It shouldn't be struck through. So the use of confidence is When a node queries you and says, do you prefer this transaction? You respond that you prefer it if there's no other transaction in the conflict set with a higher confidence. So let me break that down for a second. So in this conflict set, transaction Y and transaction Y prime, transaction Y has confidence 1 and transaction Y prime has confidence 0. So we prefer transaction Y to transaction Y prime. So if somebody asks us, hey, do you prefer transaction Y? We'll say yes. If somebody says, do you prefer transaction Y prime? We will say no. Okay? So let's keep going. There's some new transaction Z, and we do the same thing as before. We query K validators, and we get a response. In this case, again, it's an alpha majority response because we get 3 yeses. So we update the DAG, and it gets a chit. It has confidence of 1. It has 1 consecutive success, and we update the processing ancestors. And in this case, the ancestors still don't have 4 or more or 4 consecutive successes, so nobody can get accepted yet. Okay, so that's really the gist of the Avalanche consensus protocol in action, but obviously there's still a lot left undiscussed. And here is what I was saying before, where if someone asks us if we prefer transaction Y prime, we'll say no, because we prefer transaction Y, which has a higher confidence. We prefer the one with higher confidence within a conflict set. So in practice, so first, what I discussed just now is how Avalanche consensus is described in the white paper, but at Avalabs, the implementation that we've done is a little bit different. We've made some optimizations for latency and throughput. And the most important of those optimizations, maybe, is that we have this notion of vertices. So it would be kind of a lot of overhead if every transaction, if we had to vote on every single transaction at once. So we batch transactions into vertices, and vertices are basically just batches of transactions. They act pretty much the same way that transactions do in what I've just shown you. If you receive a vote for a vertex, that is a vote for all of the transactions in that vertex, and votes are applied transitively upward, right? That's like increasing your ancestors' confidence and consecutive successes upon success. So the same principles apply. And we say that a vertex gets accepted when all of the transactions in it are accepted. If a vertex contains a rejected transaction, then that vertex gets rejected. So the first line is a restatement of what I've just said. So if a vertex gets rejected, all of its descendants get rejected too. And we kind of just ignore that part of the DAG and we cease to build on it. So rejected vertices, valid transactions. So if a vertex gets rejected but has valid transactions in it, we're just going to take those valid transactions and we're going to reissue them into a new vertex, which is not the child of a rejected vertex, and continue on from there. So Avalanche consensus is probabilistic in the sense that technically you're not guaranteed safety, but you are to an arbitrarily high threshold, an arbitrarily high probability of safety. But it is final. Again, I guess technically it is probabilistically final, but basically the gist of our safety guarantee is that if any correct node accepts a vertex, then all correct nodes will eventually accept that vertex, right? If one person decides pizza, then everybody eventually will decide pizza, all of the correct nodes anyway. Similarly, if any correct node rejects a vertex, then everybody will eventually reject that vertex. And this is final and irreversible. Once something has been accepted by a correct node, you are darn sure that it is accepted by everybody else too, and that will never ever change. So this isn't like Nakamoto consensus or proof of work consensus, where You know, there's your block might be included on the chain, but then later it gets reorged and then it's not part of the chain, and you have to wait like an hour or something for your transaction to have gone through and for you to be confident that it actually is part of the history. With this, the decision is final and it works really quickly. This happens in like less than a few seconds. So there's a few other optimizations that we do. You might have thought like it's kind of weird that we just ask, do you prefer this, yes or no? And everybody responds with a binary yes or no. That's not as efficient as it could be. So what we do is instead of asking, do you prefer this vertex? Nodes say, hey, I learned about this vertex. So given that that vertex exists, which vertices do you prefer? And instead of just getting a binary yes, no back, you get what they think the accepted vertices will end up being, which helps you make progress faster. Similarly, the protocol, as I described it before, you only query upon hearing about a new transaction, but obviously you need a bunch of stuff to be happening on the network to make any progress, because you only make progress when there's a new transaction. So we don't do that, and instead the nodes just repeatedly query the network and follow that algorithm until there's no virtuous vertices processing. A virtuous vertex is one that doesn't have conflicts. If we allowed, if we had it so that we continued until there were no processing vertices at all, then that wouldn't be good, because you could just create, conflicting vertices and have the network just churn forever trying to reach consensus on them. A final optimization is that nodes don't necessarily need to wait until they get all K query responses before registering the outcome of a poll, because sometimes you can tell that nothing is going to get an alpha majority. So at that point, you don't need to wait for the rest of the responses. You can just say nobody got alpha majority votes, reset all the confidences, et cetera, or reset all the consecutive success counters. So this is a proof of stake based system. So we don't use Nakamoto consensus. We don't use proof of work. So in a world where it's free to become a validator that's part of this network, then that's problematic, because you can just start up like a billion nodes. Your nodes get queried all the time, and you as a malicious person can have those nodes do whatever you want and violate the safety and liveness threshold, right? So the validators, the nodes that are being queried as part of consensus, they have influence over the network, and they have to pay for that influence. So basically, we're tying real world value to influence over the network to prevent vote stuffing, to make sure that no one could just start up a billion nodes and, you know, break our system. So in order to make your node a validator, you have to bond or stake something valuable. And in the case of Avalanche, that's our native token Avox. The more Avox that a node bonds, the more often it's queried by other nodes, right? So it's not a uniformly random decision when you're sampling the network, right? So you have to pick K people to sample. You don't pick uniformly randomly. You do weighting based on the amount of Avox that they've staked. So if you stake more Avox, you get queried more often, you have more influence over the network. And we incentivize nodes to be validators by giving them a reward if, while they're validating, they're sufficiently correct and responsive, right? So we reward them for good behavior. And something else to note about Avalanche is that we don't have slashing. So if a node does not behave well while it's validating, maybe it gives incorrect responses, or maybe it just doesn't respond at all, then we don't burn their stake or anything like that, or reduce it. We just give it back to them, but with no reward. So this is nice in case, I don't know, your node is down because AWS had an outage or something. So as long as a sufficient portion of the bonded AVOX is held by correct nodes, then the network is live for virtuous transactions and the network is safe, meaning that, again, any correct nodes will agree on what has been accepted and rejected. So zooming out a little bit, I want to just hit on two big ideas of Avalanche consensus. The first one is the use of subsampling. So the fact that we do subsampling is really cool for the reasoning that I laid out before, which is that it has really low message overhead. So again, it doesn't matter if there's 20 validators or 2,000 validators, the number of consensus messages that a given node needs to send remains constant, which is really nice. It really allows you to build a decentralized system. And the second big idea is transitive voting, right? This idea that a vote for a transaction is a vote for all of its ancestors. And that really helps us make progress. That really helps with transaction throughput because you're essentially getting a bunch of votes for one, right? So for example, in the diagram on the right here, if you get a vote for transaction D, then that implies a vote for all of its ancestors. So even though you just received a vote for D, that also counts as a vote in favor of A, B, and C. So this helps with transaction throughput because you're getting a lot of votes for the price of one, essentially. And with consensus protocols, the thing that a lot of protocols get hung up on is the number of messages that need to be sent back and forth becomes overwhelming as the number of transactions increases. And this helps to keep that down because even if there's a lot of transactions being processed, you don't need to do a round of voting for each of them. You can just do votes on their children, and that is applied transitively upward. A few other loose ends to wrap up. How are transactions created? Good question. So users cause transactions to be created either by issuing an API call to a node or just issuing a send or an issue transaction call to a node. Maybe if you've created the transaction manually using our JavaScript library or something, for example. How are vertices created? So nodes will batch the incoming user transactions into a vertex and query the network about it, and it'll get added to the DAG that way. Or, and this isn't written here, but again, vertices can be created if a rejected transaction has or a rejected vertex has valid transactions within it. Those will be regrouped into a new vertex and issued. And another loose end is how are a vertex's parents chosen? When a node is issuing a vertex, it'll just choose a handful of parents. This is a parameter of the system. It'll choose some number of parents from the virtuous frontier. And this is nodes that are at the tip, the end of the DAG that don't have conflicts, right? This is important that we want to build upon virtuous vertices, because if we build on non-virtuous vertices, vertices with conflicts, then there's a higher chance that that vertex gets rejected and all the ones underneath it get rejected, and then we make less progress, and that's bad. So we only build on virtuous vertices. Just some other observations about Avalanche is that conflicting transactions are not guaranteed to be live, right? You might not be able to make progress on conflicting transactions. But that's actually not really a problem, because if you don't want your transaction to not be live, then just don't issue a conflicting transaction. So it's pretty much as easy as that. You only have to be worried about your transaction not going through if it has a conflict. And if it has a conflict, then that means that you presumably issue that conflict, right? So like, I can't issue a conflict with somebody else's spend transaction unless I have their private key and I can be spending the same UTXO as them. Another observation is that Avalanche works for linear chains too, right? You just do almost the exact same thing as before, except you restrict that a vertex only has one parent. So Avalanche is kind of more general than this, but you can restrict that vertices only have one parent, and that gives you a total ordering of vertices, or blocks if you want to call them at that point. You get a linear chain out of it, and that can be nice for certain applications. If you want to know, like, this came before this for every pair of transactions. Another cool thing about this system is that if there's no work to be done, then nothing is happening. You don't need to send consensus messages back and forth. You're not like churning, trying to add length to the network or anything, or to the chain. You're just sitting there kind of twiddling your thumbs, chilling out. And that's good, because proof of work does not have this feature. You constantly have to be doing work. That's a feature, not a bug of proof of work. And that's obviously really bad from a sustainability point of view. And Avalanche solves for this. And finally, there's no leader. Anyone can propose a vertex. Anyone that has staked a Vox can vote on vertices. So there's no leader, which helps make the network more robust and decentralized. So kind of wrapping up and zooming out even more, why should we care about this? So Avalanche is a general consensus engine. What I've laid out, it doesn't really matter what kind of application you're putting on top of it. This protocol allows you to decouple state management, right? The like actual application layer of what you're doing from the consensus layer. So if you're building an application on top of this, you just have to define some notion of, you know, here's what conflicts mean, here's what a vertex, or here's what a transaction is, and so forth. And you don't have to worry at all about what's underneath. You just kind of have this black box that is the consensus protocol, where you put something into it, and eventually it comes out as being accepted or rejected, and then you can move on from there. So you can use Avalanche for all sorts of applications, not just peer-to-peer payments, but for example, on the Avalanche network, we have an EVM instance running, right? It's your same favorite Ethereum virtual machine with smart contracts and Solidity and all of that good stuff. And underneath, we've basically just taken out Ethereum's proof of work consensus mechanism and plugged in our own Avalanche consensus protocol, which allows for lower latency, right? Just a few seconds between blocks, higher throughput, all that good stuff. Avalanche has really good performance. You can get in the thousands of transactions per second with 1 to 2 second transaction acceptance latency. And another thing that sets it apart is that it really is decentralized. It can support thousands of validators because of that subsampling trick that we used. And I'll say this again, proof of work based consensus protocols are really not sustainable and should be phased out in favor of non-planet burning consensus protocols like Avalanche. And with that, I will take questions. If you haven't come up with a question now, that's okay. You can email me at daniel.laine@avalabs.org. Feel free to drop me a line. I love to talk about this stuff. So yeah, with that, I'll turn it over to questions.
Hey, should we look at some questions? Someone asks, how does consensus work for off-chain transactions?
I'm not sure I understand the question. I mean, the point of the consensus protocol is to accept on-chain transactions. So I'm not sure I understand.
So I think that there's probably two parts here to the question, I assume. Tony, the person, please feel free to add more detail, but I think he's saying, probably how do you do off-chain? Is it possible to do off-chain transactions or kind of, yeah, with Avalanche? And if these were the case, kind of how do they work, and how do they get how does the consensus protocol kind of approve them? Not approve them, but you know what I mean.
Yeah, I'm not familiar with the notion of an off-chain transaction, and maybe this is where I'm showing my my consensus protocol weaknesses here, but I'm just not sure what an off-chain transaction is.
Okay.
So I'm afraid I can't answer that question.
No
Is there a box or something where I can see all the questions here? Because
yeah,
I'm just seeing.
more and then chat. They're in there.
Maybe if I exit. Okay, I see now. I had to exit out of the share screen.
Yeah. So but I will read the next ones. Someone asked, how do you run a node? That was answered. What trade-offs does Avalanche make in its design between speed, scalability, and decentralization?
Yeah, so in general, I don't like giving corny answers that sound crazy and unrealistic, but really, Avalanche, I don't think does make a trade-off between these three things, right? With classical consensus protocols, for example, you get speed, but you don't get scalability and decentralization. With Nakamoto consensus, you get scalability and decentralization at the cost of speed. But I think that really, because of the subsampling and transitive voting tricks, you really do get all three of these things. And you don't have to take my word for it, because I mean, we have a live network, and you know, we have all of those things on it. So yeah, I would say that there is no trade-off that happens really, which is the novel breakthrough of Avalanche consensus.
Fair enough. Next one. Vijay asks, is it possible that a malicious node can spam wrong responses to get the wrong outcome?
Yeah, so this has to do with the safety and liveness thresholds that I mentioned before. So as long as the malicious nodes comprise less than the safety threshold of the stake, right? If the malicious nodes control less than a certain amount of stake, then the network is safe, even in spite of malicious nodes giving whatever answers they feel like or not responding at all. So as long as the nodes don't have a sufficient amount of stake, which is, I'm not sure what we've parameterized it to now, but enough that the network is safe, even in spite of people putting up like several $100 million in stake to be malicious.
Very good. So a couple of questions. I guess I'm going to summarize them because it's a certain tone to them. So I guess the first one is that do you think by having large staking requirements, you basically make node operators basically quite large individuals that can have a lot of control over the network and make it quite centralized?
Yeah. So first, I mean, valid point. It's one thing to say that our protocol is decentralized, and it's another to have a decentralized network. So I'll point out that at this time, the network has like, I think, well over 600 validators. But the point remains, like, fair point that it costs a lot of Vox to make your node a validator right now, and we're gonna decrease the amount as time goes on. Now that the ecosystem is a little bit more developed, we're gonna keep decreasing the minimum stake requirement.
So what was the logic behind so why would you have such a large staking requirement to begin with?
Yeah, that's a good question, and I don't have a lot of insight into the answer. I think maybe one thing to consider is, you know, when we started the network, you know, all other things equal, it's easier to run a network with less nodes, which at the start is kind of what you want. You want things to be stable, and we prioritize that perhaps, and that's maybe how those the minimum staking requirement got ironed out in the first place. But now that things have stabilized, not that they were ever unstable, I should add, I think we're going to decrease the minimum stake requirement.
Awesome. How does gas work on Avalanche?
Yeah. So we have several chains that are part of the network. It's a bunch of blockchains or DAGs in the whole network. And so we have one of those chains is an Ethereum virtual machine, And we've manually set the gas price on that to 470 gigaway. There's no market for gas like there is on the ordinary Ethereum network. It's just fixed at that.
Okay, perfect. I guess a question that's relevant that it wasn't asked: what is the best wallet to use with Avalanche?
I would say our own, just wallet.avox.network.
Perfect. Awesome. I think that there's another question. How can you be sure about speed when there are? I mean, I'm going to change the tone of this question. Given how early it is in Avalanche's development, how confident can you be that when more applications, like Ethereum level type applications, are built, that the same speed will be maintained?
We've done throughput tests.
Fair. Good answer. Awesome. Guys, any other questions for Dan while we have him? It's always the awkward moment of silence at the end, really. Awesome. Dan, what was your email again in case people wanted to ask questions offline?
Daniel.Laine@avalabs.org, or you can find me on LinkedIn or whatever else suits you. Yeah, again, feel free to message me. I like to talk about this stuff. So if there's nothing else, thanks all for your time. This is a pleasure. I'm glad to be able to have been able to talk about this.
Awesome. Well, Daniel, thank you very, very much for your time today and for such a thorough kind of look at the way Avalanche's consensus works. For hackers, guys, we're in the final weeks of the hackathon, so looking forward to seeing what you build with Avalanche and with to great success, hopefully. If you have any questions, please find me on Discord. You can ask technical questions about Avalanche. We also will be recording this event, or we have recorded this workshop, this presentation, and we'll be publishing this along with the slides later this evening, hopefully, so you can digest anything and go back over it. But in the meantime, Dan, thank you once again for your time. We greatly appreciate it, and we hope you enjoy the rest of your day. And to everyone else who joined today, thank you very much, and hopefully see you all very soon.
All right, thanks. Bye all.